20 engines that were so overbuilt, they made accountants weep and engineers grin. These aren't just motors. They're monuments to what happens when perfectionism meets production lines, when durability targets get thrown out the window, and someone in the boardroom says those three magical words, cost no object. Picture this. It's 1989, and Toyota's engineers are sitting in a conference room in Tahara, Japan, staring at a blank sheet of paper. Their mission? Build an engine that would power Lexus's assault on Mercedes and BMW, not just match them, humiliate them. The result was the 1UZ-FE V8, an engine so ridiculously over-engineered that it routinely outlasted the cars it powered. We're talking about an all-aluminum V8 with 6-bolt main bearing caps, 6 bolts per main bearing when most engines make do with 2 or 4. The crankshaft? Forged steel, not cast iron like everyone else was using. The connecting rods were forged too, with fracture-split big ends for perfect alignment. Toyota's engineers specified clearances so tight that each engine took longer to assemble than some companies spent building entire cars. But here's where it gets interesting. The 1UZ wasn't designed for 100,000 miles, or even 200,000. Internal documents showed Toyota targeted 300,000 miles of smooth, quiet operation. They tested prototypes at full throttle for 100 hours straight. They ran them without oil changes for 50,000 miles just to see what would break. Nothing did. When the LS400 launched, it didn't just compete with the Germans, it made their engineers question everything they thought they knew about reliability. 25 years later, you'll find these engines still purring in clapped-out drift cars, making twice their original power on boost, refusing to die. Now, if you want to talk about refusing to die, we need to discuss Mercedes-Benz's OM617 diesel. This cast-iron monstrosity from the late 1970s and early 80s wasn't trying to be sophisticated, it was trying to be immortal. Everything about this 5-cylinder diesel was overbuilt to an almost comical degree. The block was cast iron so thick you could use it as a boat anchor. The head? Cast iron too. The injection system was purely mechanical. No electronics to fail, no sensors to go bad, just precision machined steel doing what steel does best, lasting forever. Mercedes tested these engines in the most brutal way imaginable. They gave them to taxi drivers. In Morocco, these engines ran 24/7 in 130-degree heat, with questionable maintenance and fuel that was more sand than diesel. In Germany, they accumulated 500,000 kilometers a year on the Autobahn. The result? OM617s, with over 1 million miles, became so common that Mercedes stopped considering them special. The engine's only weakness was that it outlasted every other component of the car. Body panels would rust away, interiors would disintegrate, transmissions would give up, but that OM617 would keep clattering away, indifferent to the passage of time. Let's jump forward to 1990 and talk about an engine that shouldn't exist, Honda's C30A from the original NSX. This was Honda showing off, pure and simple. They took a 3.0-liter V6 and treated it like they were building a Formula One engine for the street. The connecting rods weren't just forged, they were titanium. Titanium! In 1990, most supercars were still using steel. Each intake port was hand-polished by the same technicians who prepped Honda's F1 engines. The result was a finish so smooth that Honda claimed it improved airflow by 10% over machine finishing. But the real insanity was in the assembly. Honda built a dedicated clean room facility just for NSX engines. Technicians wore white gloves and assembled each engine by hand, signing their work when complete. Every single engine was dyno tested at the red line for 30 minutes before installation. Not spot checked. Every single one. The break-in procedure at the factory involved 150 miles of varied load running before the engine ever saw a car. This wasn't mass production. It was mechanical artistry. And it showed. NSX engines routinely hit 200,000 miles without rebuilds while being thrashed on racetracks every weekend. Then there's BMW's S72 V12, the beating heart of the McLaren F1. This engine is what happens when you give BMW M Division an unlimited budget and tell them to build the greatest naturally aspirated engine ever created. 6.1 liters, 627 horsepower, 480 lb-ft of torque, and a redline of 7,500 RPM. But the numbers only tell part of the story. The S72 had two of everything: two ECUs, two fuel rails, two throttle assemblies, essentially two inline sixes sharing a common crankcase. The throttle bodies weren't just individual. They were fly-by-wire in 1992, with each bank controlled independently for perfect cylinder filling. The lubrication system was dry sump with a separate oil tank, multiple scavenge pumps, and enough oil capacity to run Le Mans without changes. BMW claimed they spent more developing this one engine than most companies spent on entire car platforms. Every single S72 was signed by the technician who built it and came with a certificate of its exact power output. No two were identical. But wait, there's more. The Toyota 2JZ GTE might be the most overbuilt engine relative to its original purpose. Toyota designed this 3.0-liter twin-turbo straight-six for the Supra, targeting 280 horsepower due to Japan's gentleman's agreement. So why did they build it strong enough for 1,000? The block was closed-deck cast iron with oil squirters for each piston. The rotating assembly was fully forged, crank, rods, and pistons all capable of handling 4 times the stock power. The head was aluminum with massive ports and sodium-filled exhaust valves. The 2JZ's party trick was its oiling system. Toyota gave it oil passages so large that tuners joke you could lose a wrench in them. The oil pump was sized for twice the necessary flow. Why? Nobody knows. It's like Toyota's engineers knew what was coming, that 20 years later, tuners would be pushing 1,500 horsepower through these blocks on stock internals. The 2JZ became legendary not for what Toyota made it do, but for what it could do. It's the AK-47 of engines, simple, overbuilt, and absolutely indestructible. Speaking of indestructible, Lexus doubled down on the over-engineering with the 2UR GSE V8 from the ISF. This wasn't some parts bin special with a tune. Lexus built this 5.0-liter V8 like they were entering Le Mans. Forged internals everywhere, pistons, rods, crank, titanium intake valves. The assembly tolerances were tighter than most racing engines. Each engine was hand-assembled in Yamaha's specialty facility, where they also built Formula One engines. The 2UR GSE revved to 6,800 RPM and made its peak power at 6,600, unheard of for a large displacement V8 in 2007. The valve springs were made from a special alloy that Yamaha developed for their motorcycle racing program. The camshafts were billet machined rather than cast. Even the oil pan was over-engineered with multiple baffles and trap doors to ensure oil supply during high-G cornering. Lexus claimed the engine would maintain factory power levels for 200,000 miles. They were being conservative. Now let's travel back to 1989 and talk about Nissan's RB26 DETT. This twin-turbo inline-six powered the R32 Skyline GTR, and it was so advanced that it made contemporary European engines look agricultural. The block was cast iron with 6-bolt main caps and a fully counterweighted forged crank. The head featured dual overhead cams, 4 valves per cylinder, and individual throttle bodies. In 1989, the twin turbos were ceramic-wheeled units that spooled instantly, but were backed by an intercooler so large it barely fit behind the bumper. What made the RB26 special wasn't just the hardware, it was the sophistication. Nissan gave it an oil system with twice the capacity of similar engines, including a second oil filter just for the turbos. The cooling system had separate circuits for the block and head, allowing different operating temperatures for optimal performance. The engine management system could pull timing on individual cylinders if it detected knock. This level of complexity was unheard of in 1989. Most manufacturers were still figuring out basic fuel injection, and here's Nissan building what was essentially a Group A race engine for the street. Let that sink in for a moment. Porsche's Mezger Flat 6, named after Hans Mezger, the engineering genius behind it, represents perhaps the pinnacle of air-cooled engine development. This wasn't just any Flat 6. This was the evolution of Porsche's racing engines, refined over decades and put into street cars with virtually no compromise. The engine that powered the 911 GT3, GT2, and turbo models was essentially a Le Mans engine with license plates. The Mezger engine's dry sump lubrication system had 8 separate scavenge pumps, one for each cylinder bank, plus additional pumps for the heads and crankcase. The oil tank held 13 liters. The crankcase was designed to withstand the forces of endurance racing with massive main bearing supports and cross-bolting throughout. The heads featured sodium-filled valves and VarioCam Plus, Porsche's variable valve timing and lift system that could switch between 2 completely different cam profiles. These engines regularly survived track days that would destroy lesser motors, then drove home and commuted to work Monday morning. The Mercedes-Benz M120 V12 from the early 1990s is what happens when Mercedes decides subtlety is overrated. This 6.0-liter, 48-valve monster powered everything from the S-Class to the Pagani Zonda, and it was built like a bank vault. Each bank was essentially a complete inline-six with its own ECU, ignition system, and fuel delivery. The block was aluminum with cast-iron cylinder liners, combining lightweight with durability. The heads featured 4 valves per cylinder with dual overhead cams and hydraulic lifters that never needed adjustment. Mercedes over-engineered even the small details. Each cylinder had its own ignition coil, no distributor to fail. The cooling system had an electric water pump that continued circulating coolant after shutdown to prevent heat soak. The variable intake manifold had multiple runners per cylinder, optimizing airflow across the entire rev range. This engine was so robust that AMG later bored it out to 7.3 liters for the Pagani Zonda, where it made 750 horsepower while maintaining stock Mercedes reliability. Think about that, a 750 horsepower engine that you could service at a Mercedes dealer. The Volkswagen W12 deserves a special mention for being perhaps the most complex engine ever mass-produced. Take 2 VR6 engines, already unusual with their narrow 15-degree cylinder angle, and join them at the crankshaft to create a W configuration. The result was a 12-cylinder engine barely larger than a conventional V8. The engineering required to make this work was staggering. The crankshaft had to handle combustion events every 60 degrees of rotation. The cooling system needed separate circuits for each bank. The intake manifold looked like something from an alien spacecraft. But here's the kicker. Despite this complexity, the W12 proved remarkably reliable. VW used it in the Phaeton, Bentley put it in the Continental GT, and Audi stuffed it in the A8. These engines regularly accumulated hundreds of thousands of miles without major issues. The secret was over-engineering every component to handle the unique stresses of the W configuration. The main bearings were massive. The oil pump could supply a small apartment building. The cooling system had enough capacity for 2 engines. It was German engineering taken to its logical extreme. Now, the Mazda 13B REW deserves recognition not for conventional over-engineering, but for perfecting an engine design everyone else gave up on. The twin-rotor Wankel from the FDRX7 featured sequential twin turbos, a small one for quick response and a larger one for top-end power. The system was so complex it required a rat's nest of vacuum lines and solenoids that made technicians weep. But when it worked, it was magic. Mazda addressed the rotary's traditional weaknesses through sheer engineering determination. The apex seals, the rotary's Achilles heel, were made from a special carbon composite that could handle extended high RPM operation. The side seals featured multiple springs for consistent pressure. The oil injection system had multiple jets per rotor, ensuring proper lubrication even under extreme conditions. The result was a 255 horsepower 1.3-liter engine that could rev to 8,000 RPM all day long. Yes, they still needed rebuilds more often than piston engines, but for a design everyone else abandoned, the 13B Rue's durability was remarkable. Let's shift gears and talk about diesel dominance. The Ford 7.3 Power Stroke from the late 90s and early 2000s is legendary among diesel enthusiasts for one reason: it simply would not die. This wasn't the most powerful diesel or the most refined, but it was engineered with one goal: outlast the truck it came in. The block was cast iron so thick that Ford engineers joked you could make two modern engines from one 7.3 block. The rotating assembly was forged steel throughout, with main bearing caps that looked like they came from a locomotive. The injection system was HEUI, hydraulically actuated electronic unit injection. Instead of a high-pressure pump, it used engine oil pressure to fire the injectors. This meant fewer failure points and the ability to run on terrible fuel without destroying expensive injection pumps. The head bolts went so deep into the block that head gasket failures, common on other diesels, were virtually unknown. The result? 7.3 Power Strokes with 500,000 miles became so common that they stopped being noteworthy. Million-mile examples exist. Still running, still pulling, still refusing to acknowledge their age. The Subaru EJ22 might seem humble compared to these giants, but it represents over-engineering in a different way. This 2.2-liter Boxer 4 was Subaru's workhorse from 1989 to 2001, and it was built with rally-bred toughness. The closed-deck block design meant the cylinder walls were fully supported, preventing the distortion that plagued open-deck designs under boost. The cylinder walls themselves were ridiculously thick, so thick that builders could bore them out 10 millimeters and still have plenty of meat left. The bottom end featured a forged crank and connecting rods that could handle twice the stock power without modification. The head gaskets, traditionally Subaru's weak point, were multi-layer steel on the EJ22 and rarely failed. The timing belt was non-interference, meaning if it broke, you just installed a new one and kept driving. No bent valves, no destroyed. Pistons. These engines routinely hit 300,000 miles in harsh climates where other engines would have given up after 150,000. They weren't exciting, but they were anvils. The Mitsubishi 4G63T tells a similar story of hidden strength. This 2.0-liter Turbo 4 powered everything from the Eclipse to the Lancer Evolution, and it was built like Mitsubishi expected owners to double the boost on day one, which, let's be honest, they did. The early 7-bolt versions had massive main bearing caps that could handle 500 horsepower on stock internals. The later 6-bolt versions, while controversial, were actually stronger in some ways, with improved oil squirters and better rod bolts. The 4G63's real party piece was its ability to handle abuse. The factory turbo cars came with forged pistons and rods, not cast units like competitors. The ringlands were thick enough to survive detonation that would destroy lesser engines. The head was aluminum, but with massive cooling passages and sodium-filled exhaust valves. This engine became the darling of the DSM tuning community because it could handle 400 horsepower on stock internals with just bolt-ons. Examples with 200,000 hard miles are still making big power today. Going bigger and tougher, the Toyota 1HDT diesel inline-six from the Land Cruiser might be the toughest engine ever put in a passenger vehicle. This 4.2-liter turbo diesel was designed for one thing: surviving where survival seemed impossible. The Australian outback, the Sahara Desert, the Amazon rainforest, places where a breakdown doesn't mean calling, te ole. It means death. Toyota's engineers assumed the worst about everything. They assumed the fuel would be contaminated with water and sand. They assumed the air filter would be clogged. They assumed maintenance would be performed by someone with a hammer and good intentions. So they built the 1HDT to survive all of that. The injection pump was mechanical and could run on basically anything flammable. The turbo was sized for reliability, not power. The cooling system was massive, with a radiator that looked like it came from a semi-truck. The result was an engine that would run forever on fuel that would kill a modern diesel in minutes, in temperatures that would melt lesser vehicles, with maintenance intervals measured in years rather than months. When Chevrolet created the LS7 for the C6 Corvette Z06, they didn't just want to make power, they wanted to embarrass European exotics with American engineering. This 7.0-liter, naturally aspirated V8 made 505 horsepower while meeting emissions and warranty requirements. The internals were pure racing hardware, titanium connecting rods and intake valves, unheard of in a mass-production American V8, forged aluminum pistons with oil squirters for cooling, a forged steel crank that could handle 8,000 RPM pulls all day long. The LS7's dry sump oiling system was borrowed directly from the C5R race car. It had a separate oil tank, dual pressure, stages and scavenge pumps that ensured oil supply even under sustained high G cornering. The CNC ported heads flowed like nothing GM had ever mass-produced. The sodium-filled exhaust valves could handle exhaust temperatures that would melt conventional valves. This wasn't just a big displacement bruiser, it was precision engineering that happened to have an American accent. The fact that tuners are now getting 1,000 naturally aspirated horsepower from built LS7s shows just how much strength GM built into the design. BMW's S54 straight-six represents the pinnacle of naturally aspirated six-cylinder development. This 3.2-liter screamer powered the E46 M3, and it was essentially a racing engine detuned just enough to pass emissions. Individual throttle bodies for each cylinder, a setup usually reserved for race cars. Double Vanos variable valve timing on both camshafts, forged internals throughout. The red line was 8,000 RPM, but the engine was strong enough to handle 9,000 with software changes. The S54's bottom end was so overbuilt that BMW used essentially the same design for their P54 race engine, which made 450 horsepower from the same displacement. The oil pump was upgraded from the already stout S50 with increased flow and pressure relief. The cooling system featured an electric water pump that could vary flow based on temperature and an oil cooler that looked like it came from a much larger engine. These engines are known for being maintenance intensive, but when maintained properly, they'll deliver 200,000 miles of 8,000 RPM thrills. We can't talk about over-engineered American muscle without mentioning the Chrysler 426 Hemi. This engine wasn't just powerful, it was built to handle power levels that wouldn't be common for another 40 years. The hemispherical combustion chambers that gave it its name weren't just for show, they allowed for massive valves and optimal flame propagation. The block featured cross-bolted main bearing caps, something you'd only see on race engines at the time. The rotating assembly was forged steel throughout, with rods so beefy they looked like they came from a diesel truck. The 426 Hemi's rocker arms were mounted on individual stands, not a common shaft, allowing for precise valve train geometry even under extreme spring pressure. The dual four-barrel carburetors weren't just for show, the engine needed that much fuel flow to support its power potential. Original 426 Hemis are now making 1,000-plus horsepower with basic modern upgrades like fuel injection and better cylinder heads. The fact that a 1960s design can compete with modern engines shows just how overbuilt the original was. Honda's K20A from the Civic Type R and RSX Type S represents modern over-engineering at its finest. This 2.0-liter four-cylinder made 220 horsepower, naturally aspirated, 110 horsepower per liter from a production engine in 2001. The secret wasn't just VTEC, but the obsessive attention to detail throughout. The intake ports were designed using Formula One technology. The combustion chambers were CNC machined for consistency. The valve train featured roller rockers instead of conventional followers, reducing friction and allowing for more aggressive cam profiles. But the real over-engineering was in the bottom end. Honda gave the K20A forged pistons and shot-peened connecting rods in a naturally aspirated engine that wasn't meant for boost. The oil pump was sized for racing use. The cylinder walls were reinforced with iron liners in an aluminum block. Why? Because Honda's engineers couldn't help themselves. The result is an engine that can handle 400 horsepower on boost with stock internals, rev to 9,000 RPM for hours on end, and still get 30 mpg on the highway. Finally, let's talk about the Cummins 6BT, specifically the 12-valve version from 1989 to 1998. This 5.9-liter inline-six diesel wasn't trying to be sophisticated. It was trying to be the last engine on Earth still running after the apocalypse. Everything about it was mechanical. The injection pump, the fuel system, even the throttle. No electronics meant nothing to fail. The block was cast iron so thick that people used them as engine stands for other engines. The head was held on with massive bolts that went deep into the block. The gear-driven camshaft meant no timing chains or belts to fail. The 6BT's injection pump, the legendary P7100, was mechanical artwork. It could be adjusted with simple tools to make anywhere from 160 to 600 horsepower. The engine's rotating assembly was so robust that 500,000 miles was considered broken in. Million-mile examples aren't rare, they're expected. These engines have been adapted into everything from boats to generators to rock crawlers because they'll run on basically anything combustible and survive conditions that would destroy modern engines in minutes. So what makes an engine over-engineered? It's not just strength or power, it's the refusal to compromise. It's building in capabilities the original buyers would never need, but future generations would worship. It's engineers asking, what if, instead of how little? It's the difference between building something to last the warranty period and building something to outlast civilization. These 20 engines represent different philosophies of over-engineering. Some, like the Mercedes OM617 and Cummins 6BT, achieved immortality through simplicity and brute strength. Others, like the BMW S72 and Honda C30A, reached it through obsessive precision and exotic materials. Some were over-engineered by accident, like the Toyota 2JZ, which became legendary for capabilities Toyota never advertised. Others, like the Porsche Mazda, were deliberately built to racing standards for street use. What unites them is that they were all built by engineers who were given permission to do their best work, not their cheapest work. In an era where engines are designed by accountants and built to be replaced, not rebuilt, these 20 stand as monuments to what's possible when durability matters more than the bottom line. The tragedy is that we'll probably never see their like again. Modern emissions requirements, fuel economy standards, and the shift to electrification mean that the era of the over-engineered combustion engine is ending. These engines aren't just mechanical marvels. They're the last of their kind, reminders of when built to last actually meant something. But perhaps that's what makes them so special. In a disposable world, they're permanent. In an age of planned obsolescence, they're defiant. They're proof that with enough engineering talent and corporate will, you can build something that doesn't just last. It improves with age, gains character with use, and becomes legendary through survival. Every one of these engines has stories, of cross-country runs that should have been impossible, of track days that should have been fatal, of neglect and abuse that should have been terminal. But they survived, thrived even, because someone, somewhere, decided to build them right instead of cheap. That's over-engineering at its finest, building in a safety margin so large that it becomes a legacy. What's your favorite over-engineered engine? Have you owned any of these indestructible legends? Drop a comment below and share your stories. Because at the end of the day, these engines aren't just about specifications and horsepower, they're about the memories they've created and the adventures they've enabled. And that kind of engineering never goes out of style.